seminar, and look forward to your talk. Thanks.
All right, should I start? Okay, thank you so much for the invitation. I'm very happy to be here for the first talk of 2025. So what I'm going to talk about, the symmetries of rings from hyperplane arrangements. I guess this is sort of a vague or broad title because it's like a topic that I'm interested in a variety of contexts, but what I'm going to be talking about today is joint work with two grad students, Meg and Chang-Lee at Brown and Trevor Karn at Minnesota. And so I'll be talking about like the symmetries of a specific hyperplane arrangement and rings that come from that. So the big idea of what I want to talk about today is sort of broadly thinking about I guess a philosophy that I like to think of in a lot of my work, which is that sort of studying sequences of integers that are interesting and appear in combinatorics is actually oftentimes the shadow of some algebraic thing that's going on. In particular, what we're actually like sometimes the reasons these integer sequences are interesting is because they're actually counting the dimensions of spaces that are in and of themselves interesting. And we can go even further and think about not just these sequences as counting dimensions of spaces, but also of those spaces having symmetries, and so these integers are actually counting dimensions of representations on interesting spaces. So that's sort of the overall philosophy that I want to hopefully demonstrate today. And the sequences of integers that we're going to be thinking about today are the ones that come from hyperplane arrangements. So things like the coefficients of the characteristic polynomial of a hyperplane arrangement and the number of chambers in particular. Okay, so what I'm going to do is I'll first tell you about the cohomology rings that I'm interested that come from the complement of a hyperplane arrangement. So there's sort of two families of rings that you can think about, the Orlik-Solomon algebra and the Varchenko-Gelfand ring. So I'll tell you about those. I'm going to really focus on the Varchenko-Gelfand ring. So apologies if you already know about that, because I'm going to sort of go
Is it me or did we lose our speaker? I think we lost the speaker. Oh,
I
no.
think yes.
Well, she knows where we are, I guess. It seems like a bad day for Zoom.
Hi, sorry.
Good.
Okay, let me start again and hopefully.
Your
Okay,
video is frozen, Sarah.
talk about
But we,
the vertigo. I'm still frozen.
yeah, but we can hear you at least.
Okay, can you see my cursor?
Yeah.
Okay, but I'm frozen.
Not anymore. Yeah.
Okay, all right, just keep me posted about.
We'll let you carry on. Hopefully it clears up.
Yeah. Okay. All right. So, so I'll tell you about these cohomology rings, and then I'll tell you about the symmetries that arise from them, and then I'll tell you about sort of I want to illustrate two examples. So the braid arrangement case, this is, I'd say, like the classical case that we understand as much as one could possibly understand about these rings, at least so far. And I want to use this as like my prototypical like goal of what we would want for arrangement. And then I'll talk about that Megan Trevor and I are looking at the threshold arrangement, which is a much more difficult arrangement to sort of get your hands on. Okay, so I want to start with thinking about these cohomology rings. And the setup here today is going to be that I have some real hyperplane arrangement, and it's going to be central, which means that the hyperplanes intersect at the origin. So here are two examples of real central hyperplane arrangements. And one sort of integer sequence that we're going to be interested in is the number of chambers, which is the number of full dimensional cones that these arrangements cut out. So you can see in this case, these are my chambers. They're maximal dimensional cones. And there's 6 of them in this case, and 8 of them in this case. And in general, I'll write the number as C of A. Okay. And we're going to be thinking about the complement of these spaces, and there's sort of 2 natural ways that you can think about the complement. So the first way is thinking about the real complement. So these are hyperplane arranged planes that live in real space, right? RK. And so the real complement is really just going to be I take my hyperplanes and remove them from the space. So like you can really visualize this. This is like I have R2 and I'm just removing these lines. And when I do that, I get a disjoint union of contractible pieces, right? These cones or chambers are just contractible. So in some sense, this is like topologically a boring space because it's just, right, this disjoint union. And so that means that its cohomology ring is just going to be concentrated in degree 0, and it'll have the dimension as the number of members. But it turns out that this ring, even though it sort of seems topologically boring, has a really interesting presentation, which is called the Varchenko-Gelfand ring. So I'll tell you about that soon. But for now, what I want to note is that this ring has the presentation that's interesting is via what's called Heaviside functions, which are certain types of linear functionals. And this ring is not graded, but it has a natural associated graded ring that also has a cohomological interpretation. So you can get some sort of ring from this. Okay, and then the second complement is, I think, maybe more studied. So this is the complex complement, which is I take my hyperplanes, I embed them in complex space, and then I remove those hyperplanes from a copy of C to the K. Okay, and so this sort of as a topological space is more immediately interesting because it's not just a disjoint union of contractible pieces, and its cohomology ring has a very nice presentation. It's isomorphic to what's called the Orlick-Solomon algebra of the arrangement. So this is, I think, a very well-studied algebra. It's graded naturally. So in cohomological degrees, it'll be concentrated in degrees like 0 to 4 up to 2K. And its total dimension, again, will also be the number of chambers of the arrangement.
So, sorry, question.
Yeah.
That's I guess that's not the usual grading, since you know in topologically it's generated in degree 1, right?
Yeah, so I guess if you can think about the cohomological generator as in degree 2, but if you wanted to just think about it as like a exterior algebra modulo relations, then you could think about that generator in degree 1, and then it would just be like 0 to K.
So that's like the weight filtration, um, as opposed to the topological degree or something.
Yeah, yeah. And I guess I'm gonna be a little bit loose with like I'll basically what I care about, yeah, is like the 0, 1 to K up instead of like keeping track of this cohomological degree. Yeah. Other questions? Okay. So why do we want to study these rings? Well, I think they're a very nice example of sequences of integers that we care about actually recording like this algebraic phenomenon of like dimensions of spaces. So in particular, the chambers of the hyperplane arrangement we saw give the dimensions of both of these rings, the Orlick-Solomon algebra and the Varchenko-Gelfand ring. But even more refined, about the characteristic polynomial, some sort of combinatorial function that you can associate to your hyperplane arrangement. The coefficients here are giving the dimensions of the graded pieces of the Orlick-Solomon algebra and the associated graded Varchenko-Gelfand ring up to sign. So this characteristic polynomial is based on if you take the hyperplane arrangement and you look at the lattice of all intersection subspaces or the lattice of flats. This is a function you can sort of define for any lattice. But in the case of a hyperplane arrangement, we really care about the coefficients. Okay, so the sort of prototypical example, as I said, is going to be the braid arrangement. So this is a hyperplane arrangement where the hyperplanes are the set ij, where I'm saying xi is equal to xj, or xi minus xj is 0, for all possible I and j. And here's a picture when n is 3. So this is a two-dimensional hyperplane arrangement. And you can see, so here are my 3 lines. And the number of chambers is n factorial. So this is the dimension, this will be the dimension of both the Varchenko-Gelfand and Euler-Solomon algebras. And you should really think about this like n factorial as counting permutations. And these permutations, I've written them down in the chambers. So the chambers are very naturally indexed by permutations. And the way that I get this, the way that I write this down is if I start with like the chamber 1, 2, 3. So I label this permutation. Every cross over a hyperplane, I permute the numbers that correspond to this hyperplane. So like 1, 2, 3, when I cross over H1, 2, I swap 1 and 2. Okay, and the characteristic polynomial has this very nice expression. So it factors into this product of linear terms, but I can also express it, the coefficients, as the Stirling numbers of the first kind. So these count the number of permutations in the symmetric group that have J cycles. So you should think of this as refining this permutation information. So I have, in general, my dimension will count the number of permutations. And now each graded piece is sort of is refining that information by the number of cycles the permutation has. Okay, so now I want to tell you about what this Varchenko-Gelfand ring is and how we get its associated graded. So we're thinking about the real complement here. And so every hyperplane I can think about as dividing my space into two pieces because we're in this real complement. So we can see that here, like I have a hyperplane, it's cutting the space in half, so I can think about this as one side and this as the other side, okay? And what I'll do is I'll choose arbitrarily a positive and a negative part for my hyperplane. So in this case, I'm going to say that this side is the positive part of my hyperplane. And so the Varchenko-Gelfand ring is going to be generated by linear functionals on this real complement. And these linear functionals are called Heaviside functions, okay? And so here's how they work. So for every hyperplane, I'm going to have a Heaviside function, which I'll write as lowercase hi. So it'll be a map from this real complement to the integers. And what I do is I take an element in the complement, so like let's say an element here, and I send it to 1 if it's in the positive part of my hyperplane and 0 if it's in the negative part. So we can think about this at the level of chambers because it's the same on every chamber. I can think about this linear functional as have a number, a 1 on this chamber, a 1 on this chamber, and then zeros over here. Okay, and so they're actually elements of the zeroth cohomology space, which is where the whole cohomology ring is going. Okay, so the nice thing about notations. The sort of nice thing about these Heaviside functions is that they form an algebra by addition and multiplication pointwise. So I'm going to show you this with an example, the braid arrangement. So in this case, the Heaviside functions are going to be indexed by hij because that's how my hyperplanes are indexed. And so I want to show you an example of what is 1 minus h12 in this ring. Well, I'm thinking about these as linear functionals. So the function 1 is just going to take 1 on every chamber. And then h12, I'm going to say this is the positive part, so it'll take 1 on this side and 0 on this side, okay? And then I just do the sort of most naive thing. I go chamber by chamber, and I'm going to say, okay, so 1 minus 1, that's 0. And so I'll have zeros all over here, and I'll have ones, because this is 1 minus 0, I'll have ones underneath this line. Okay, and so this is what 1 minus H12 looks like. Okay, I can also multiply these. And again, I'm going to do it chamber by chamber. So here, let's say I have H12 times H23. And I want to multiply chamber by chamber. I look at like this chamber times this chamber. This is 1 times 0. And so I get a 0. Similarly, 0. This chamber here is 1 times 1. So I'll get a 1. And everything else will be a 0. Okay, makes sense. Okay, and so what Varchenko and Gelfand proved is that these Heaviside functions are used to give a presentation of this cohomology ring. So in particular, there's a surjection from, I take the polynomial ring in generators indexed by my hyperplanes, and I send them to these Heaviside functions, okay? And so the kernel of this map is going to be generated by certain circuit relations so relations that depend on the combinatorics of the hyperplane arrangement. And we can define the Varchenko-Gelfand ring as this polynomial ring in the generators modulo these circuit relations. So I'm not going to tell you sort of explicitly what the circuit relations are, but I'm going to show you by example in a second. Okay. So I claim that actually these circuit relations are kind of intuitive to see when you write them down at the level of Heaviside functions. So for example, I claim that this is in the kernel of the braid arrangement, and we can see why. So if I do Z12 times 1 minus Z12, this is Z12, right? So it's 1s up here and 0s below. And then 1 minus Z12 is the opposite. So they're supported on opposite things, and so when I multiply them, I get 0. Okay. And similarly, if I can multiply these this product of 3 Heaviside functions or 3 monomials, this is also in the kernel. Because okay, so if I multiply H12 times H23, we already saw that this is just I would have like this chamber have a 1 and everything else has a 0. But again, this support is disjoint from that, this support of 1 minus H13. And so what I get is, again, the 0 function. So these are examples of 2 things that would be in the kernel of this map. Okay, and so the braid arrangement, we can write down very explicitly these, like all the circuit relations. So it sort of simplifies because it's a very nice arrangement. So this Varchenko-Gelfand ring is generated by these 2 relations. So the first relation is the one I showed you. So Zij times 1 minus Zij, which I can write as expand it as this. And then the second one is, so this was the example I showed you, but it turns out to generate the kernel, I need to take a sum of 2 different things. So these 2 terms here, and if I expand that out, you can see that I get 2 terms that cancel. So this cancels with this, and so I just get this sum of 4 terms. And again, this is like the fact that there's only 2 relations here is a product of the braid arrangement having a very nice circuit structure. But in general, you would have like much more complicated circuit relations, and you wouldn't necessarily be able to, write them all down in such a compact list. Okay, so this is not a graded ring, right? These relations are not homogeneous. But there is a way to turn this into a graded ring. And so that's how we get the associated graded. So in particular, there's going to be a filtration on this Varchenko-Gelfand ring. And the filtration is I take, if I let Fi be the monomials of degree I in those Zij generators, in degree I or less. Okay, so then I get an ascending filtration. You should think of this like Fi plus 1 has monomials of degree I plus 1 or less, and so it definitely contains Fi. And the associated graded formally is I take a direct sum of these quotients. But today I'm more interested in trying to give intuition for this. So the intuition behind this associated graded ring is before when I was looking at the Varchenko-Gelfand ring, I was quotienting out by non-homogeneous relations. And essentially what I want to do is I just want to take my relations and make them homogeneous, like force them to be homogeneous by only considering the highest degree term. So that's like the effect of what happens when I take this quotient. So I'm going to show you by example. So in the braid arrangement, we said that these were our two relations, right? And so what I'm gonna do is I'm really just gonna like cross out the lower degree terms. So this is, I would cross out this degree one term here, and again, this degree one term here. And now these relations are actually homogeneous. And this is now a presentation for this associated graded ring of the braid arrangement. So I mod out by the squares of the generators and this quadratic relation here. Any questions about this?
So these form a Grosvenor basis? Is that
Yeah, so there's a Grosvenor basis. Yeah, the Grosvenor basis is given by NBC sets of the arrangement.
so it's
So the
just
basis,
like in the Orlick-Solomon case, but
exactly. Yeah. And I'll get to that in a second, sort of the similarities of those two presentations. Other questions? Okay. So this associated graded ring, if you remember, I'm thinking about my hyperplane arrangements as being in RK. This graded ring is going to have K plus 1 graded pieces, again from 0 to K, just like the Orlick-Solomon algebra. And this is how I'll write the jth graded piece. So now it's a commutative, it's a commutative ring, right? It's a quotient of a polynomial ring, a polynomial in these generators. But its Hilbert series, if I just look at the dimensions, exactly matches the Orlick-Solomon algebra. Again, if I sort of ignore the cohomological grading and just think about degree grading. And actually, this ring also has a cohomological interpretation. So this is a work of Moseley, who showed that I can think about this associated graded ring as the cohomology of this space here, which I think of as like the R3 thickened complement of the arrangement. So I take my hyperplanes and I tensor them by R3. I tensor my whole space by R3, and then I remove these now subspaces of the arrangement. Okay, so there's some way to think about this cohomologically as well.
so that
Okay,
is a 3 there.
why is there a 3 there?
There's a K, but I think it's a 3.
Um, so there should be a 3 here and a K here, I think. Because the idea is
Oh, the
you
ambient
tensor your whole
the
space
rank of
by,
yeah.
yeah, so you like it doesn't make sense to, yeah, basically because you're thickening everything by R3. So I could also write this as, and actually any odd number bigger than 3 would be the same, but okay. So then there's the Orlick-Solomon algebra, which I think people are a lot more familiar with. And I'm not going to go into too much detail about this because I really want to focus on the Varchenko-Gelfand ring today, but I'll just show you by example what the Orlick-Solomon algebra looks like for the braid arrangement. What you should notice is that it looks very similar. So it also has generators indexed by hyperplane arrangements, but now it's an exterior, like it's in the exterior algebra, so it's an anti-commutative ring. But it has a quadratic relation that looks almost identical to the Varchenko-Gelfand quadratic relation. I no longer have to quotient by the squares because I'm in an exterior algebra, so that's sort of automatic. But this is what my relation, or this is what my braid arrangement Orlick-Solomon algebra looks like. And the upshot is you can really, if you're familiar with the Orlick-Solomon algebra, and less so with the Varchenko-Gelfand ring, you can really think about this associated graded ring as a commutative analog of the Orlick-Solomon algebra. And the presentations you can really think of as like, I take generators indexed by hyperplane arrangements and I mod out by certain circuit relations. So the dimensions of the graded pieces give coefficients of the characteristic polynomial in both cases. Both have Grosvenor bases given by NBC sets. So sort of, I like to think about these rings as like siblings. And I think this one is the Orlick-Solomon algebra is like a little bit better known. But we'll see that the Marchenko-Gelfand ring also has a lot of nice properties. Okay, questions about this? Okay. So now I want to sort of enhance our study of these rings and the corresponding hyperplane arrangements by thinking about um, hyperplane arrangements that have symmetry. So I think most of my favorite hyperplane arrangements have some form of symmetry. And what I mean by that is some sort of finite group that acts on the hyperplanes, which will then induce an action on both complements. So for example, the symmetric group famously acts on the braid arrangement, right? So we could think about it, the transposition 1, 2 acting on these hyperplanes, like it would act on, it would send the hyperplane x2 equals x3 to x1 equals x3. So it's acting on the indices of those variables, and it would send x1 equals x2 to itself. But then it also acts on the space, right? If I have a point here, the transposition 1, 2 will reflect over this line over here. Okay, and so because all of these rings are coming from cohomology, when I have an action on the space, this will induce a representation on the rings. So the way you should think about a representation if you're not super familiar is that it's just some sort of group action on a vector space. So for example, S3 is going to act on this Marchenko-Gelfand ring just by acting on the indices of the generator. So 1, 2 here will, if the generator, or sorry, the indices are 1, 3, and so this will send 1 to 2, so this becomes a 2, and 3 to itself. So it'll just send Z1, 3 to Z2, 3. And I can also act on, linear combinations. So 1, 2, in this case, it would act on, both monomials. It acts on every single monomial. Okay. Okay, so why do we want to study the symmetries of this ring? This is sort of the natural next step in this path. We started with thinking about these sequences of interesting integers as actually counting dimensions of interesting spaces. And now those spaces have sort of natural symmetries. And so we want to understand those symmetries and actually think about them as representations on these interesting spaces. Okay, so how can we describe these representations? So I guess a dream scenario for me would be to describe these representations in terms of what are called the irreducibles, or the smallest building blocks of the representation. So this is like the smallest thing you can break down a representation into. And I guess there are other really nice ways that you can describe a representation. So for example, a lot more is known, I think, about like long-term stability properties of these rings. So Mir, I think, is here. He pointed me to, he has a paper that looks at like representation stability of subspace arrangements. And so the rings I'm talking about today would be examples. And in the context of the threshold arrangement, Proudfoot and Ramos also have looked at representation stability. So there's a lot that you can say about long-term behavior. But what I want to think about today is some sort of precise description of like every graded piece. That would be like the goal. But this is sort of a hard thing to do. So this is even for the braid arrangement, this is kind of computationally infeasible. So I'll say a little bit more about that in a little bit. So that's one complication, is like we can't always write down irreducible decompositions, even for the arrangement that we think of as being like the nicest arrangement that we know of. And then also, even though the Marchenko-Gelfand ring and the Orlik-Solomon algebras seem sort of very closely related at the level of their presentations and their combinatorics, at the level of representations, they're very different, and not in a like non-trivial way. So there's some technical way that you can relate the graded pieces of these rings, but not very explicit. You have to do it as an induced representation, and so it's not really, in terms of getting some sort of irreducible decomposition, it's not really like possible. So really this breaks it into two questions, like studying representations of the Orlick-Solomon algebra and studying representations of the Varchenko-Gelfand ring and its associated graded. So these two have the same representations, but they differ from the Orlick-Solomon algebra. So what I'm going to focus on today is the Varchenko-Gelfand ring and its associated graded.
Just a question, Sarah.
Yeah.
So I guess it's all about the grading, right? Like the if you forget the grading, then you just permute the chambers or something and you get the regular representation. Um,
So
so
that's
then
not true for the Orlick-Solomon algebra.
no, for the Varchenko-Gelfand. But then that it's still totally mysterious, where the um, isotypic components in what degree they would live in this associated graded. Is that right?
Yeah, exactly.
Yeah, thanks.
Yeah. Um, yeah. And so yeah, so the total representation even for the Orlick-Solomon algebra is not the same. But then yeah, within this this associated graded will decompose the total representation on the Varchenko-Gelfand ring, as Graham's saying. Okay, other questions? Okay. So now I want to tell you about the case where we know the most, which is the braid arrangement. Here it is again. I've drawn it now a couple of times. And remember that chambers are indexed by permutations, which you should, and so the chambers, so the total number is n factorial. And the symmetry here is that the symmetric group acts. And so to describe the representations on this ring, we need to understand a little bit about the representation theory of the symmetric group. And it has a very nice representation theory. So in this case, the irreducibles, or smallest building blocks, are indexed by partitions, by integer partitions. So this is how I'll draw my integer partitions. So this picture, which has 2 in the first row, 2 in the second row, and 1 in the third row, is the partition 2, 2, 1. And so I haven't told you exactly, of course, how to think about these partitions as corresponding to the irreducibles, but you should just think that if I want to get some sort of irreducible decomposition, what I really care about is like which partitions appear, basically. And the dimension of these irreducibles is given by the number of standard Young tableau of shape lambda. So I'll show you this by example. Let's say my partition is 2, 2, 1. I claim this representation is 5-dimensional because this corresponds to the 5 fillings of this diagram with the numbers 1 to 5 such that things are increasing across rows and down columns. So for example, here this is going 1, 4, 2, 5, 3. That's increasing across rows, and then 1, 2, 3, 4, 5 increasing down columns. Okay, and this is the 5 ways that I could do that. Okay, and then the sort of second thing that we need to know about representations is that we can actually encode them as symmetric functions via what's called the Frobenius characteristic map. So this will take an irreducible representation and send it to what's called the Schur function. And as a special case, it'll send the trivial representation, which corresponds to the partition with just one part, and send it to the homogeneous symmetric function, which is defined like this. Okay, so if you're not familiar with symmetric functions, the sort of main takeaway here is just that a rephrasing of my dream scenario in the case where I'm dealing with symmetric group representations is, instead of saying, oh, I want an irreducible decomposition, I'm going to say, oh, I want to understand the Frobenius characteristic, and in particular, an irreducible decomposition would be the same thing as being able to express my representation in terms of Schur functions, or what's called a Schur expansion. Okay. Okay, so what's the Frobenius characteristic of this braid arrangement Varchenko-Gelfand ring? So like Graham said, this has a sort of very nice, not so hard to see answer, which is so as a symmetric function, it's h1 to the n, or I can rewrite this with Schur functions as I take all the partitions lambda and I get a Schur function there, and the coefficient of that Schur function will be the number of standard Young tableau of shaped lambda, or the dimension of the representation. So this has another name. It's called the regular representation of the symmetric group. And it is sort of a very nice and well-known representation. It has a basis indexed by permutations. And I would say it's like the most natural equivariant lift of the number n factorial. Like if you asked people that study representation theory, the symmetric group, like what's your favorite representation that has dimension n factorial, I'd be very surprised if they didn't say the regular representation. Okay, and here's an example. So h1 cubed, I can expand this in terms of these three Schur functions. And again, these coefficients are coming from counting standard Young tableau. Okay, so the upshot here is, we start with n factorial. It's the dimension of this nice ring, and it's also the dimension of the Frobenius characteristic of that ring, which is h1 to the n. Okay, so what about the graded pieces? This is a much harder question. So we know the dimensions of these graded pieces are given by the Stirling numbers of the first kind. So these are the number of permutations with j cycles. So for example, when n is 3, here are my 3 Stirling numbers and the permutations that they're counting. So for example, this is 3, 1, the number of permutations that have 1 cycle. So there's 2 of them, and this is the dimension of the degree 2 piece of my ring. The number of permutations that have 2 cycles, there's 3 of them, and this is the dimension of my degree 1 piece, and similarly, this is the dimension of my degree 0 piece is just going to be the identity. Okay, so what about the representations? So work of Sundaram and Velker showed that you can describe these representations, the Frobenius characteristic, in terms of a sum of certain symmetric functions, which I'll call Thrall's higher Lie characters. So it's a sum of them indexed by partitions. So what are they? So there's some sort of decomposition of the regular representation, which is good because that's the representation we're trying to decompose. And they can be expressed as symmetric functions in this way. I don't want to go into too much detail here because this expression is known as a plethism of symmetric functions. And it's a major open problem in algebraic combinatorics to try to expand like an expression like this into Schur functions. And I think some people think that it's impossible to do in general. So in some sense, this is like this higher Lie character is like the best we can do. But it's sort of like, at least right now, totally unobtainable to try to express these graded pieces in terms of Schur functions. But here's an example when n is 3. So here we have our dimension, and here the higher Lie characters. So because n is small here, we just have like one of them for each graded piece, but in general, we'll have a sum. And because n is small, I know how to like decompose them into Schur functions, but in general, we have no idea. But importantly, they do give a decomposition of this expression the regular representation. Okay. Questions about this? Okay. So now I want to tell you about my work with Megan and Trevor, which is studying the threshold arrangement, which is a different arrangement that also has symmetric group symmetry. But it's sort of like a much more unwieldy arrangement. So the threshold arrangement, it's defined as taking the sum of xi plus xj equals 0. So here's a picture when n is 2. I just have this one line. And here's a picture when n is 3 that I tried to make. Yeah, so there's a picture. Oh. Okay, so why study this arrangement? It actually appears in connection to a lot of other interesting math. So for example, things like neural networks and algebraic statistics which might not obviously seem related. It's a special case of what's called the resonance arrangement. So this is, I think, a very interesting but like difficult to understand arrangement that we don't even know how to count the number of chambers in the resonance arrangement. So this is like a sub-arrangement of that. And then finally it has a very nice chamber count, which is where it gets its name. So its chambers are counted by the number of labeled threshold graphs on n vertices. So I'm going to tell you right now what a labeled threshold graph is. So if you haven't heard of threshold graphs, they're very well studied in enumerative combinatorics. There's a whole book about them, threshold graphs and related topics. And it has lots of, I think they were actually first introduced in connection with linear programming. But they're defined by sort of constructing a graph with using two operations. So the two operations you're allowed to use are you can create an isolated vertex or a connected vertex. So for example, let's say I want to build a graph with 5 vertices using these two operations. So isolated is what you would expect. I just like put a single vertex in. So I have isolated 1, isolated 2, okay, and then my vertex 3 is connected, which means I connect to the vertices that came before. Then I have an isolated 4, and then I have a connected 5, so I connect this to all of my other vertices. Okay, and there's my threshold graph that comes from this sequence. Okay, and so there's a way to think about the chambers of this arrangement as bijecting with these graphs. Okay, and so these graphs are sort of important in enumerative combinatorics, and many people have studied how to count them. So now we have something already like more complicated than, with the braid arrangement, we were just looking at permutations. And we said there are n factorial permutations, which is sort of a very simple expression. Now we don't have a simple expression for the number of chambers. Instead, what we have is an exponential generating function. So if I let Tn be the number of labeled threshold graphs, a work of Bissinger and Peled proves that the threshold graphs have this exponential generating function expression. Okay. And then there are also two well-known recursions for these threshold graphs. So here are two recursive ways of getting the number of labeled threshold graphs. Okay, so with Megan and Trevor, what we're trying to do is make these statements equivariant, right? So we're starting with now the number of labeled threshold graphs. That's the dimension of the Sverchenko-Gelfand ring, and now we want to understand sort of the equivariant story. And again, the equivariant story is going to have to do with the symmetric group. So it will act on these arrangements in the same way that it acted on the braid arrangement, like just by permuting the indices of my variables. And that will induce a symmetric group representation on this ring. And so we want to understand, what does this representation look like? Okay, so if you remember, this is my my expression for the number of chambers. And so the first thing we do is give an expression for this representation in terms of an equivariant exponential generating function. So let's let Tn, the script Tn, be the Frobenius characteristic. Then this epsilon of x is going to be our analog of the e to the x. And what we proved is that this threshold representation has a generating function given by this expression. So you should, compare these. They should look very similar. So this is, we can call this the threshold representation now. Okay. And you might wonder, does it seem like this exists for the Orlick-Solomon algebra? And the answer seems to be no. This seems to be like, in the same way that the Varchenko-Gelfand ring of the braid arrangement is the regular representation, and that's not true for the Orlick-Solomon algebra. in this nice threshold representation is describing the Marchenko-Gelfand ring, but there's not an analogous statement for the Euler-Solomon algebra. Okay. So we also have equivariant expressions for these recursions. So the first one, this is our first recursion, and we prove that this has this nice lift at the level of the Marchenko-Gelfand ring. We can get at the nth representation recursively from smaller threshold representation. So for example, if n is 2, this is the representation, and so I can use this recursion to figure out what n equals 3 is, and by following this expression. Okay, and then the second recursion, which looked like this, it turns out this actually governs the what are called the branching or restriction rules for this Marchenko-Gelfand ring. So if f is a symmetric function, one thing I can do to it is take its partial derivative with respect to p1, which is a power symmetric function. And this has a representation theoretic meaning. The meaning is looking at the restriction from Sn to Sn minus 1. And so what we proved is the second recursion, the equivariant lift of the second recursion is actually telling us branching rules about the restriction from this representation of Sn to Sn minus 1. Questions about any of this? Okay. So you might wonder, okay, what about the graded pieces? And I think this is a very hard problem. So actually, even just the dimensions is a hard problem. So it was a problem in EC2 by Richard Stanley to combinatorially interpret the coefficients of the characteristic polynomial of this threshold arrangements using like the combinatorics of threshold graphs. So to give an expression for these coefficients. And this was answered only very recently by Deshpande, Menon, and Singh. So they described the characteristic polynomial coefficients in terms of what are called odd anchors of threshold graphs. So here's an example. I'm not going to go into the exact definitions, but here's an example of the bijection that they give between the dimensions of and these odd anchors. So the odd anchors are in blue. And here's the Frobenius characteristic, which looks pretty simple in this case, but actually when n gets bigger than 3, things get really crazy. And it's actually a lot harder to understand. Okay, so this sort of gives way to some harder problems about trying to understand the graded pieces, which if anyone has ideas about this, I would be very interested because I think these graded pieces are really interesting, but they're very hard to pin down. So what I would like to know is some sort of basis for this ring in terms of threshold graphs. So we have a way of thinking about threshold graphs as counting the dimensions of the graded pieces, but I would like to upgrade the story from just dimensions to some sort of algebraic statement about a basis of rings. And then I also would really like to understand the representations on the graded pieces of this ring. Like even, where do the trivial representations live? But in general, it would be very nice to have some sort of expression for the graded pieces similar to these higher Lie characters that we saw for the braid arrangement. And so, okay, so we haven't been able to do this yet, but what we have been working on is trying basically to understand this Marchenko-Gelfand ring as much as we possibly can. And so one thing we've been able to do is give a simplified presentation of this ring. So in a priori, there are sort of like a ton of relations that this ideal that we need so the Marchenko-Gelfand ring is this quotient of circuit relations, and in general there are like many circuit relations. So we saw with the braid arrangement we could write it down compactly with just two relations, and so we've done a similar thing for the threshold arrangement. So this is the last thing I want to say, which is that what our presentation looks like. So I'm going to think about defining a monomial using a graph. So I think it's better to just see it with an example. So I'll think about an edge in a graph, an edge from the vertices I to j as telling me about the monomial zij. So for example, this cycle here that's labeled 1, 2, 3, 4 would correspond to this monomial. So z12 comes from this edge, z24 here, z34 here, and z13 here. Okay, and so what we proved is that the only relations that you actually need to generate this ring are labelings of the square. So things that look like these quadratic relations, and then labeling of what we call this dumbbell. So this dumbbell with just a triangle and then one edge between it. So it's a very small list similar to the braid arrangement. Okay, so here's a summary of like sort of contrasting these arrangements. So we saw that the braid arrangement, the chambers are n factorial, they biject with permutations. Threshold arrangement, chambers are biject with threshold graphs. The Frobenius characteristic of this braid arrangement is the regular representation. Whereas for the threshold arrangement, it's this threshold representation, which is new. The characteristic polynomial has combinatorial interpretations in both cases. So the Stirling numbers of the first kind counting permutations with by number of cycles tells us about the braid arrangement, whereas the number of odd anchors of a threshold graph tells us about the threshold arrangement. And then finally, the Thralls-Hyer-Lee characters tells us about the braid arrangement, but this is like a big mystery. What happens equivariantly for the graded pieces of the threshold arrangement. Okay, thanks.
Thanks, Sarah. Questions?
I have some questions. Oh, sorry, Ahmed, you can go ahead.
You go ahead, Chris.
Okay. So first, thanks for the very nice talk. I have a few possibly very stupid questions, but my first question is, are there any special cases? So you have the Varchenko-Gelfand ring and then the associated graded, but are there any special cases where the Varchenko-Gelfand ring is graded? So, or in particular, where the associated graded and the graded are equal?
I think if the arrangement is rank 0, because basically the reason that the Varchenko-Gelfand ring is not graded is you can think of it as it's the cohomology ring of a bunch of contractible pieces, and so it's just going to be in degree 0. Whereas so it's basically impossible for it to be graded.
The reason I ask is it reminds me of something that you can do with fans and cohomology of torque varieties. Like one way to get the cohomology of a smooth torque variety, for example, is to take the polytope and to take its normal fan, and then instead of defining, well, one way to think about the cohomology is you can identify the what do you call these? The characteristic functions, not of the full cones, but of the rays. And so in some sense, I think that is the doing the same thing, except with if you take the hyperplane arrangement corresponding to the polytope, and there it is a graded ring. Anyway, sorry, yeah, maybe that didn't make a lot of sense, but so it's never graded. Okay. My next question is you said the Orlick-Solomon algebra is like the abelianization of the Varchenko-Gelfand ring, is that right?
Other way around. Or
Yeah, right.
I don't know, maybe abelianization isn't quite accurate, but it's sort of like
Ah,
um
is it the case, something like the Orlick-Solomon algebra is like the full cohomology ring with the odd degrees included, and so it's like graded commutative, whereas the Varchenko-Gelfand is the even degree piece. Is that what's happening here?
um so you can think about, I think like uh so in the Orlick-Solomon algebra, the cohomological degree is like the okay, so in both cases you can get a presentation um by thinking about the pullback of the fundamental cost of a sphere. Um, and in the case of the Orlick-Solomon algebra, the sphere is it's like a even or sorry, an odd dimensional sphere, and in the Varchenko-Gelfand ring, it's a odd dimensional or even dimensional sphere. And so somehow like the cup product, like because they live in different cohomological degrees,
Right.
um, like that's really governing the commutativity versus anti-commutativity. So that's more how I think about it as like you have like very similar things happening, but you're pulling back spheres in different like of different dimensions. And so that's sort of how it's coming. I don't know if that answers your question.
Uh, sure, yes. Yeah, sort of. Okay, that's fine. And then my third question, sorry, is you showed these tables where you compute the Frobenius character of the associated graded and then
Hmm.
the Frobenius character of the regular.
Hmm.
Maybe this is a completely stupid question, but should I always expect the sum of the Frobenius characters of the associated graded to be equal to the Frobenius character of the original? Is that stupid?
Yes, as long as you're working in characteristic zero. So as long as your representation is semi-simple, that's true. I
Okay.
think
Is that some
if you
theorem in
were working
representation?
in a different characteristic, I don't think that that would be guaranteed. But because, um, yeah, so basically because you're in characteristic zero.
Is that a general fact from representation theory? Do you know, or
Yeah, I believe so. That if you're working characteristic zero and you have an associated graded where like the filtration respects the group action, then the representations will be the same. So you have to check that like the action is
ah,
preserved in the
okay,
filtration, but then yes.
okay. That's great. Okay, thank you, and thank you again for the very nice talk.
Thanks for the questions.
More questions?
Hi, thank you for the talk. And you say that the Verchenko-Gelfand ring and the Orlik-Solomon algebra are not isomorphic as a representation.
Hmm.
What about the top degree of the graded Verchenko ring?
Yeah, that's a good question. So the top degree is they're isomorphic up to tensoring by sign. So basically, there's a way to think about to relate them as induced representations, but then at the top degree, you're not actually inducing anything. And so that's why you can like explicitly relate them. So yeah, like for example, the braid arrangement, the top degree is the free think the multilinear component of the free Lie algebra. And I think the Orlick-Solomon algebra is that, but tensored by sign, or possibly the other way around. But that will always be true. I guess it won't, depending on the representation, it'll be, um, it's like it's always tensored by a one-dimensional character. And I think if it's the symmetric group, it will be tensored by just sign.
Okay, thank you.
Mhm.
Sarah, can you tell me what the minors look like in the threshold arrangement or the structure of the face poset or
Yeah, so that's one thing that we have also done. I guess I didn't include that, but we've been looking at the even the lattice of flats was not known, or at least we couldn't find it for this threshold arrangement. So that's one thing that we've been sort of doing in with the goal of like understanding this arrangement as much as possible is combinatorially describing the lattice of flats. And in that case, so the threshold arrangement is a sub-arrangement of the like type B arrangement. And there's a combinatorial way of thinking about that lattice of flats in terms of like signed set partitions. And so you sort of have to carefully think about what happens when you are only looking at certain hyperplanes and like looking at certain subspaces. But basically you can think about it as some types of like the flats are indexed by signed set partitions subject to certain conditions. So that's the lattice of flats. The base poset, I guess would be similar. I think it would be instead of set partitions, it would be set compositions.
Is there a way to say that you've got like little threshold arrangements that get assembled together to make say flats in the big one? Or that's probably too simplistic, but you know, like for the braid arrangement,
Yeah,
those plathistic formulas come about because you know, you sort of have like little braid arrangements living inside.
yeah, exactly. This is, I think, where the threshold arrangement is much harder, is that it doesn't seem to have this like nesting quality. Yeah, yeah. So I've been looking for things like that, but I haven't been able to find anything like that. And it's like, for example, it's not, yeah, so a lot of the properties of the braid arrangement that we use do not follow or are not part of the threshold arrangement. And that's one of
So-
them.
Sorry, Sarah, would you mind showing the definition of the threshold arrangement again?
Yes. Yeah, so it's like if you thought about the type B arrangement, you would have like these lines as well.
Ah, you're missing the coordinate. Ah, I see. Okay.
You're missing the coordinate and then you're missing this one as well. And so, okay, it's kind of tricky because when n is 2 and 3, it looks very nice and simple, but then as soon as n is 4, like the number of chambers is kind of a strange number. Like the number of chambers here is 2,